everyone to making sense of ductless heat pump systems. This course is approved for 1 hour in continuing education units, GBCI, AIA, HSW, NARI Green, Certified Green Professional, AIBD, and may be applicable to your local or state-based design or contractor license. My name is Brett Little. I'm the Executive Director here at the GreenHome Institute, and I'll be your moderator today. GreenHome Institute is a nonprofit with a mission to make healthier and more sustainable choices in the renovation and construction of the places we live. And a huge shout out to all of those who support our work and allow us to do what we do. Huge thanks to our big sponsor, Anderson, volunteers, presenters, and our board of directors. Huge thanks to all of them. So with that, I'm going to introduce our presenter, Ken Nelson from Panasonic. Ken is over on the other side of the world from us, on the West Coast, and he has been with Panasonic working both in ventilation and ductless heat pumps for the last 8 years. He consults with builders, architects, engineers, as well as he's working with energy raters and building science professionals both nationally and throughout the Northwest. Ken has spoken at universities, colleges, builder groups, and basic building science groups as well for at least the past 5 years. So with that, Ken, feel free to take it away.
All right. Brett, can you hear me?
Yes, we can hear you.
Okay, good. So thanks everyone for coming in, and I think we'll just get started. I wanted to cover real quick. We're going to do, because it's kind of the obligatory acronym description thing, the first couple of slides are just going to talk about the different acronyms that you're going to see. The HSPF, which is the heating season performance factor, and why they're relevant. So there's HSPF, there's going to be the SEER and the EER. But the HSPF is primarily for heating climates, and quite frankly, it's set up around rebates, right? So if you have an HSPF value that is appropriate, you can maintain or get rebates based on the HSPF. If you are in the southern climates, then you have SEER, the seasonal energy efficiency ratio, which is how you get your rebates for air conditioning. So having said all that, it's really just kind of a benchmarking system for ductless heat pumps to kind of give a value to them. And we're going to talk more about why that's good and bad and stuff in a minute. But then there's also the EAR, the energy efficiency ratio, which is just more funky math that not many people are paying much attention to today in the building, because it doesn't represent any rebate values. So, but HSPF and SEER values are all indicative of rebate values. So the other acronym that we'll talk about is COPs, the coefficient of performance. COPs are an interesting function, and what happens with the COPs is that they'll tend to lock down the condenser, and it's kind of a disadvantage for ductless heat pumps, because we're using an ECM motor that can move up and through the continuum of speed and output. But to measure a COP value, you simply have to lock that down so that the heat pump doesn't go up and down. So I'll give you kind of an example here, I think. Differences. So you're going to see two different systems here. Both are 12,000 BTU systems. And these are, of course, all Panasonic, because this is what I have the data for. But the XE is our top-rated model, and the RE is our lowest-rated model. And then you'll see a rated value and a max value. And almost all of your manufacturers, when you go to the service manuals, will give you the rated value and a max value. And the rated value is what they're going to give to AHRI, and we're going to talk about AHRI in a second. But so what you're going to see is, let's go over here on the left-hand column to 47 degrees, where that XE gives you a COP of 4.2 at rated value, but it only gives you a 3.2 at max value. And then the lower cost application will give you a 3.85 at the rated value, but it'll give you a 3.49 at its max value. So when I say max, that's maximum output. For example, if you were, if it was, just on high, if you were to take, let's say it's 47 degrees outside and you put the indoor unit on 80 degrees, that's going to speed up that compressor, or try to, but the rated value says it's only going to be at that 4.2, and the rated value is fixed at 47, and so you can't, in a 68 degree indoor, you can't really tell what the high speed is going to look like from there. So, and you can see there's different capacities, and this is kind of how they come to terms with the COPs, is you have the wattage, capacity wattage, and then the input wattage, and then the output BTU, and then from there there's a math function that gives you the output COP. One of the things I wanted to show you here was that on this XE, this is a minus 15 degree application. However, at minus 14.8 tested, your COP over here to the right is less than 1. So, and basically a electric resistance heat is a COP of 1. So quite frankly, you could go to, at minus 14 degrees, you're financially better off to go to electric resistance heat. Even though the ductless heat pump will go that low, you're technically losing money by using a ductless heat pump at minus 14 degrees because the COP is below 1. And then the other thing that you'll see is you'll see the BTU output drop out. So 3,500 BTUs, you're probably seeing a heat load requiring considerably more than that at that temperature. So while all of the manufacturers can go low, or not, I shouldn't say all of them, they can all go to a minus 4 anymore. And minus 14.8 or minus 15 is a big stretch, but your output is going to be diminished, and quite frankly, you'd have to check your individual COP values, but most likely you're better off with electric heat at that temperature. So that's kind of the fuzzy part of COPs. That you can see it's a sliding scale. At 75 degrees, I don't need much heat at 75 degrees, but my COP is great. I live at the 46 degree, between 35 and 46 degrees is where I want to be. So in this case, it's a 2.6, 3.2. So when someone starts, a manufacturer starts telling you how great their COPs are, the question is, COP at what point? I mean, anybody can do a good job at 75 degrees. The money in ductless heat pumps is at 35 to 46 degrees value. So another term that we'll talk about a little bit is called diversity, and diversity applies to multi-zone applications where I might have 2 or 3 or 4 heads. So what happens with a multi-zone is I can add, if I have a 5-zone system, I could put 5, even though I might only have a 56,000 BTU output at the outdoor condenser, I could put 5 24K heads on there. So, however, ultimately I'll only get the 56,000 BTU out of the condenser. So what we talk about with diversity is, and think in terms of the house, as the sun goes from east to west, I might require heating in one part of the house, and I can load up on that side, and then as the sun moves across, I might require heating on the other side of the house, or I might have a room that requires heating at one point of the day but not the other. So diversity is the ability, it's probably just a big word for a zonal heating application, but in the air conditioning world, the HVAC world, they like to call that diversity. So we can move heat or cooling around the house at the occupant's whim, if you will. So everything that when I talk to builders and so forth, when we talk about ductless heat pumps, I advocate that they go look at AHRI. When you talk about system performance, go look at AHRI. AHRI is a third-party vendor, and as a manufacturer, I'm here to tell you I can spin information about Panasonic stuff like nobody's business. But the reality is, the AHRI is a third party, and they're going to give you a better, unbalanced or unbiased, I guess you would say, look at what you're looking at. And it's pretty easy to go in and compare products. So as we go through, there's the website here below, but you're going to pick up, under the residential section, you're going to pick up variable speed mini-split and multi-split heat pumps. And then you'll click there and you go to the next page, and then you can fill in the particular model or type that you're looking for. And then over here on the right lower right corner, you're going to see this crazy number that you've got to fill that in to make sure that they're not being spammed. But in any respect, you can do whatever criteria you want, or by manufacturer or whatever, and then it will process up and say, these are all of those applications. It'll tell you if it's a current system, if it's an active system or a discontinued system. It'll tell you the type, the indoor type, whether it's a non-ducted or a multi-split, mini-split, or excuse me. And then it'll start giving you all of the data, the cooling, the high heating. And my favorite is, as I go here across the page, is low heating, right? So what's the BTU output at 17 degrees? When we, okay, so let's go. There's single zone systems, and they can be 5, 7, 9, 18,000, 24,000, 36,000 BTU. If you really want to throw money at it, you can go to the VRF stuff, which is even higher, but there's not much in VRF in single zone, but they can get even higher. What we look at, and I go back to the AHRI listing, is when I talk to builders, our concern is never, you know, how it performs at 47 degrees. Every heat pump that you look at will be better than electric heat at 47 degrees, no matter what. I mean, they're all good. However, the criteria is what happens at 17 degrees, because at some point in time, we almost always will see some low temperatures in our world. And for a builder, and we have to be conscious of the builder's pain points, but the builder doesn't want to do is select a product that is going to put him at risk for getting, you know, if he builds 25 houses and all of a sudden it drops down to 20 degrees outside, he's got 20 potential customers calling up saying, hey, your heat pump's not giving me enough heat, my house is freezing. So what I do is when I go through there, and this is, you know, and one of the things I like about our Panasonic products is that AHRI rating at 17 degrees. There is no better rating. We have a good, better, best. The best gives you a 12,500 BTU output at 17 degrees. And you'll hear a lot about Fujitsu and Mitsubishi and so forth, all of those from the manufacturer. And I counsel my builders, go to AHRI and see what their actual tested output is, because we'll say a lot of things, but the third-party testing really is where the rubber meets the road. So when I'm looking for BTU output, when I'm counseling with builders about what they're looking at, you want to make sure that you can have the output when it gets cold, because if it's too hot and the air conditioning doesn't keep up, people get a little sweaty, but they still don't call the builder. But if they're cold, if people get cold, that builder is going to be, his phone's going to ring. So this is one of the critical pain points that I discuss with builders, is when you're looking at making a selection, go to the AHR website and look at 17 degrees. I don't care about 47 degrees. I don't even care about HSPF hardly anymore, because everybody does a pretty good job with HSPF. And in the Northwest, you know, we don't have a big SEER issue. Our air conditioning is so, you know, interesting story in Seattle. I think the last statistic I saw was less than 10% of the residential occupied spaces have, less than 10% have air conditioning. So obviously SEER is not the biggest thing in our day. But down south, it's a different story. So we look at 17 degrees, because when it gets cold, no one's happy. So we also have multi-zone systems. Multi-zones are a lot of fun. So I have 3 houses. I have one with a single head. I have 2 with multi-zones. I have a 3,500 square foot house, and it has a 5-zone outdoor condenser with 3 wall mount indoor units. And I have the house I live in has a 2-zone outdoor condenser and 2 indoor wall mounts. One of the caveats about these systems is that you have to have at least 2 units to make any of them work. Even though I have a 5-zone on my other house, I could actually make that system work with 2 indoor units, and as many as 5. So, and they can be a combination of the wall mounts, the ceiling cassettes, or these low profile. And we're going to come back to the low profile, because a low profile has a lot going on with with indoor air quality and ERVs and how we can mate that up to ERVs and HRVs to get your indoor air quality AHRI standards met. So let's see here, that's the multi-zone. So key components for multi-zones, again, there's your output and heat. And I typically, again, I'm kind of biased towards heat here in the Northwest because that's what we do. But here's your high heat, and they all perform pretty darn respectable at 47 degrees. But again, my concern typically comes down to what's the output at 17 degrees. So when I talk about sizing, and I try to stay away from being the official sizing, but I look at what's my heat loads requirement at low temperature. It wouldn't do me any good to put a 28,000 17 degree unit in if I need 36,000 BTUs. So that is going to be kind of a conflict, right? So we want to, or what I would want to have is I'd want to have some sort of redundancy heat control, whether it's a stick heater or who knows what. But we just, here's a good example. We just put this 4-zone system. We just put a bunch of these in Kotzebue, Alaska. And we looked at the 4-zone versus the 5-zone, and I get more BTUs. No, I don't even get more BTUs on the high end. I get the same amount of BTUs. So we went with the 4-zone because it's considerably less money. But we were looking for that 28,000 BTU output at 17 degrees. Now, in Kotzebue, Alaska, their COP becomes a 1 based on their price of gas, becomes a 1 at about 33 degrees. So literally, they're going to turn these off at 33 degrees and just go to gas heat. However, above 30, from 33 to 60 degrees, these things make them nothing but money, and they're thrilled about it. I, on the other hand, probably less so, because one of my challenges in Kotzebue is that the natives have never used ductless heat pumps, and they're put in multi-zones. One caveat about a multi-zone system is that you have to have all the heads have to be in either heating mode or air conditioning. I can't put one head in air conditioning and one head in heating. So if you put one in a room that gets a solar heat gain and that they decide it's too hot and they don't want to hit air conditioning, it'll give you an error code. So it can be somewhat problematic. Hang on one second, I see a question. So they don't see.
Yeah, Ken, I was looking at this question, Ken, and I wanted to take it more of a broad approach than specific. If I had to look at it, I would say maybe the question is, if someone has a specific question in mind as far as what they're trying to accomplish, if they need AC, what their climate zone is, could they go to AHRI and determine from there, put in some of their inputs and then have it spit out some recommendations on what they need to do?
No. Well, you could put in your criteria, and AHRI will give you a selection of products that fulfill that criteria. Okay? So, but it's not going to tell you which is the best system. It'll just give you the list of products that are meeting that criteria that you're looking for. So, you know, because the best system, it's hard to define what a best system is, right? I mean, for one person, this might be the best system, but another person could have a whole different house, and now all of a sudden the wall mounts don't work, or the cassette does work, or, you know, so forth. So there's no such thing as a global best system. There's what's right for you. What you're going to look at is what is your cooling load requirement. And once you know your cooling load requirement, find out what devices are giving you, and what style do you want. I mean, there's a certain personal style to it, whether it's the cassette or the concealed or the wall mount. So when you say best, I'm not sure we can say what's the best. That AHRI will tell you how to meet the requirement that you ask for as far as BTU loads. They won't tell you, they'll tell you what will meet that requirement. They won't tell you what would be the best selection. Does that make sense?
Makes sense to me. We'll see if anyone else has any questions.
Yeah. So next thing we do is we go to moisture, because one of the things that that we have to use caution with, and I don't know if many of you were on the AHRI that Jeff Klinowski did last week, but we talk about bringing fresh air in. The new codes require fresh air changes, mechanical air changes in the property, right? So, which can bring in moisture, and it can actually exhaust moisture depending on where we are outside. So I tend to wind up with my old favorite here, the psychrometric chart. So we're going to look first at what happens. Boy, this one got cluttered up, didn't it? They had to change some of my slides around. We're going to look what happens in a cooling climate first, right? So if I have a 90-degree temperature outside, and I have, boy, it missed my chart, 70% relative humidity, it's basically 2/100ths of an ounce, or 2/100ths of an ounce of water. So basically it's grams, but of water in the air. These may not work because you're not going to be able to see that. So if I lower that temperature to 68 degrees via air conditioning, when that air comes in the house from 90 degrees outside, 70% humidity, and I lower that temperature to 68 degrees, it's essentially becoming rain. So it rains inside. So the ductless heat pumps will also take and move moisture out of the air. So what you're going to look for in the ductless heat pump, and you're going to have to go to the manufacturer because moisture, when it comes to moisture, there's two strategies. You either have to heat the air up so it holds more moisture, or diminish the amount of moisture in the air. So what you're going to want to go to, and this is just a copy out of our catalog here, it'll tell you, every manufacturer's catalog will tell you the moisture removal component, and that's pints, how many pints per hour. So in this case, a 9,000 BTU indoor head can remove 1.3 pints per hour. The 12,000 can do 1.7. 18,000 can do 3. I think it's 3.8. 3, yeah. And the 24K can do 7.4. I believe that is. It's a little fuzzy. Sorry about that. So that's an important component when you're in our southern climates. If you're off of a lake, or you're somewhere where you get these big moisture loads, that's huge, especially high temperature moisture loads being injected into the house with an air conditioner is simply going to turn, like I say, it's going to turn that stuff to rain, and then it's going to fall to the floor, and then you're going to have moisture mildew issues. In a heating climate, and I apologize, these slides got mangled a little bit. In a heating climate, it's a little different, right? So here in the Northwest, we spend, quite a bit of time at 68 degrees, and if you were to look, I don't know. Hey, Brett, can they see the mouse as I move it along? Where
let's here.
So there's 70% humidity at 68 degrees. Okay, so that's basically 1/100th of a gram of water in the air. So when I go to heat that up, or excuse me, when that cools down, I should say, to 57 degrees, again, it becomes rain. So you say, well, my house will never be 57 degrees. So let's go, this is my favorite image. This is an infrared shot. This is my house, and I have ductless heat pumps. And if I truly had, and this is a 48 degree outside, right? So it's 48 degrees outside. And I have a max temperature of 69.3 degrees because the ductless heat pump's on at 70 degrees. I have a minimum of 58.2, but what we saw in that previous slide was that I have rain at 57 degrees. So as long as I'm above 57 degrees, life is good at 70% humidity. However, people will say, well, my house never gets that cold, but if you look at this infrared and see the soul plate, someone didn't do a very good job with their thermal breakdown here. So all of a sudden, I'm very, very close to having condensation. So I have to manage, at all times, I have to manage my moisture load in the house, right? And I have to be conscious of how cold I allow that to get, because the minute that thing, or the second that thing hits 58 degrees, if I'm 70% in the house, I'm going to have moisture loading up there. So, and this is huge. Especially here in the Northwest, or anything in our normal climates, because we wind up with either poor or non-existent thermal breaks in these older houses, and then you'll put a setback furnace, and this the setback furnace is, as far as I'm concerned, is probably the kiss of death to a lot of multifamily and lower income properties, because what happens is, and we just had this case in Yakima, Washington. In Yakima's high desert area, low humidity outside. However, in the multifamily property, they would go in and there was a large population in a small footprint. It was an 800 square foot unit. There was 40 of them, I think it was. And they'd shower in the morning. Everybody would go to work or go to school or whatever. And as soon as they left the building, everything shut down. The heat shut off. And this is in the wintertime, the heat shut off. The furnace or the electric baseboard heats, they shut all that off because it was all on setback. And by the end of the winter, and these units were all weatherized last fall. And I think they were finished out in September. By March, when I was called in to go in and look at why the fans weren't working, these things literally had jail bars on the walls where the mold and mildew had attached itself to the walls, and the fans were failing because they'd shut everything off, and the moisture would go to the fan can where it was touching the ceiling, where it was outside of the insulated space, I should say, and condense on that and fill the back of the fan with water. So literally that setback was allowing condensation just to continue to build up on that property over and over, and they finally wound up health department red tagging it, and there was 40 people that had to be displaced because it was no longer livable, all because they didn't manage the moisture content in the unit. There was no evacuation once everyone left, and the heat and temperature was going up and down. The units that were next to them, where they installed ductless heat pumps, where they had admonished the occupants to set it at a temperature and let it sit there, no setbacks, had not a single bit of mold or mildew in that unit. So, and that was the same, in my opinion, the same failed ventilation strategy that they had, where there was no ventilation other than when they had motion in the room, but they had no mold and mildew because the temperature never allowed that place to get to that point. So I advocate we stay away from setbacks, because all we're going to do is allow these corners and crevices in a cold temperature where the poor thermal break is. And quite frankly, there's no statistical advantage cost-wise with a ductless heat pump, that if I lower the temperature 4 or 5 degrees and then try to recapture that, with a ductless heat pump, they're so efficient going lower and slower than going up and down. There's no cost difference or no statistical cost difference. Now, it might be different when I get down in the low 20s or something like that, but the way the ductless heat pump works is it heats the mass. So here's a register head right here, right? And you can see the max output's around 112, 113 degrees. And literally you can see the stud walls behind that and the nails and so forth. But when they run at consistent temperature, this is 10 feet away. So it's 72.5 degrees, 10 feet away. At 20 feet, it's 72.2 degrees. So we lose 0.3 of a degree in 20 feet. And what happens is it winds up heating the mass and keeping the mass at temperature. And as long as the mass is at temperature, the room will be at temperature. So this is an interior wall. So if you go to the back side of this wall, it only had lost like less than 0.3 of a degrees. It was down around 71 degrees on the back side of the wall. So that room was a little chillier, but certainly there was much less than a 3-degree delta in that room. So this is the left side wall at 70 degrees. That's an exterior wall, I believe it is. And then the right side wall at 70.9, that is an interior wall with some artwork on the front of it. So the objective here is we heat the mass, and the mass holds temperature. But if we allow the mass to cool, then it takes twice as much to move that temperature up and down. So the second component of that is if we do heat the mass, what about air distribution? So there's a couple of ways that we've been doing. We have a number of builders out here. In particular, probably the big one is D.R. Horton down in Portland. D.R. Horton takes these Whisper Green Selects, and they set the variable speed at 30 CFM, and they'll literally set them, I'm going to bounce, sorry about that, folks. They'll set them on that ceiling area right above the indoor wall unit. So what happens is they're taking that, basically that 100-degree air, because by the time it gets up there and diffuses, the temperature's going down. The temperature's dropping as soon as that leaves that room. So that air is somewhat diffused in temperature, but it's still 100 degrees, and then they move that across that wall so that air is now moving into the other room. So that's an inexpensive way to move. Now this particular fan runs that 30 CFM at about 2.5 watts of energy. So literally it's invisible to the occupant, and it just rolls that stuff across. So they like that. It's also got a high-low switch, so if I wanted more air in the other room, I can literally flip the switch, and now it'll go to the 50, 80, or 110 CFM value, and I can move more air. So that's one option. This is probably the most efficient option, and most efficient energy-wise and least expensive. Option number 2 that we see, all right, come on. There we go. Is this whisper value. Now the whisper value, we see this in vertical installs. So what we'll do is we'll put this on the wall, on an interior wall, as high as we can get it. And then I literally have a transfer box. We'll drive that down, we'll drive that air down through the chase. It's basically in a duct inside the chase, the wall cavity chase, and then exhaust that out to the bottom. And I can bring that out to the other side. So if I have a fan on this side of the wall, I can drive that air down, and I can exhaust it out on this opposite side, or I can exhaust it back into the room and create that thermal loop. If we see a lot of these in basements where you have split levels where they have an unfinished basement and they'll put a pellet stove in there and they want to move air from one room to the next. I see this on scissor truss construction where they have a scissor truss, a great room is in a scissor truss. So you can get a 6-degree temperature delta from floor to ceiling in a tall scissor truss area. So they'll put that fan at the top of the scissor truss on an interior wall and drive it down back into the same room or back into a different room. And that's pretty efficient. In this case, I do like I got to tell you, I've seen 50, 80, and 100 CFMs, but my favorite is going to be the 50 because it's considerably quieter. And the only, and you just don't get enough airflow difference between the 50, 80, and the 100. The 100 CFM tends to make way too much noise. So for example, at 50, you won't hear that over your TV. 100 CFM, you will hear that over the TV. Let's go. Oh, and this is probably the best application. The issue with this application, though, is there's a cost issue. This is a slim ducted heat pump, and we met with Lennar Homes and several builders who are actually building this into their architectural deal. So what happens with the slim duct is that you can literally, this has an exhaust air where the heat comes out, and now I can duct that into the different bedrooms, right? So I'll put a cover over this with a 3-duct outlet, and I can move air into 2 bedrooms and a bathroom. Let's say if I were upstairs and I wanted to put air into the 2 bedrooms and a bathroom, I can duct that right in there. They need to be a short-run duct run, but they're a duct run nonetheless. But on the inbound side, we can take and move and marry up the inbound air off an ERV or an HRV into that inbound side, and literally I can let that run. One of the ways that the ductless heat pumps work is they have thermistors on the supply, where the supply air comes in, so that the ductless always measures the air temperature coming into that indoor coil. So if that indoor coil temperature is up or down or sideways, it modulates and adjusts. So this is an ECM motor, so this will cycle up and down based on temperature and what's coming into the inside air. So if I put an ERV or an HRV, which is attached to a fresh air system, and I drive that air through there, I never see enough delta. So one of the caveats about this is it will only accommodate about a 30-degree delta. So if I want 70 degrees out, I have to have 40 degree better air coming in, which with an ERV, I'll never see a 30 degree delta, or an HRV, I'll never see a 30 degree delta. So as far as I'm concerned, for fresh air, to move fresh air, this is by far the best application. It just costs more money. Because now I can put air at temperature, at the demand temperature, fresh air at demand temperature into the room. It'll be dehumidified and filtered before it gets there because it's coming through the ERV, HRV. Now, as far as ERVs and HRVs is concerned, I never recommend HRVs in our lower 48 states unless I'm up against the coastline. If I have a high moisture value, that's one thing. I will do an HRV there. But one of the caveats about heat pumps is that they tend to strip moisture out. So we wind up with bigger issues with too little moisture in the house. Remember that moisture is generally created inside the house as we shower, as we cook, as we just do our everyday functions. Moisture is created inside the house. So the air from the outside typically doesn't have to be as strained from moisture as it does have to be from, say, dust and bugs and other critters like that, unless you live on the coast. It's a whole different story if you live on the coast. I am all good with HRVs if you live on the coast, because what happens on the coast is you get high moisture, high temperature, and you get a little bit of a wind, and that'll literally drive moist air into your house. So if you're if you're a 3 air change per hour on your house, and you get the wind blowing at 20 or 30 miles an hour with a high temperature, high moisture, it's going to literally drive that moisture load into your house, in which case you need to continuously filter that out. But for the most part, for the rest of our lower 48, moisture is more of an issue coming from inside the house than it is from outside of the house. So we do an ERV, which balances the moisture levels. So this is going to be a more costly application, but it's more predictable. You know, in ventilation, we talk about the difference between passive and mechanical, and the difference is mechanical ventilation is both predictable and uneventful. And it would be the same case here. Temperature, fresh air and temperature would be both predictable and uneventful. I can drive air into those rooms, fresh air into the rooms, meet all my code requirements for air change per hour, and have on-demand temperatures for the occupants. So let's see here. So this is our new ERV. This is 50 to 100 CFM ERV. We can take this and marry that to that application and meet all of those requirements. And I think that's about it. If you have questions on any of those, you can certainly ping me at kennelson@us.panasonic.com. And let's go to a quick question, Brett. I see one here on.
Ken, why don't we talk a little bit about retrofits? I know we talked a little bit about this yesterday, but I know a lot of folks, see their existing gas furnace system, probably have a junky or low SEER AC if they're doing heating or cooling, and they might be looking at either going completely ductless or, as we talked about, integrating a ducted heat pump system. So I guess what would be some of the pros and cons of, going to that versus, or those two different options versus an existing gas furnace and conventional AC?
Well, it's going to come down to a function of cost. When you look at what you can get done with it, from the building science component of it, I like the fact that the efficiencies occur inside the envelope with the ductless heat pump. So the energy, the heat energy and the cooling energy actually is created within the house. So one of the challenges with a ducted system is that as soon as you put that up into the uninsulated space, and if it's in the insulated space, I'm good with that. But if it goes into the uninsulated space, you wind up, let's say you're in a cooling climate down south, and you put a cold air ducted system through the attic that's not inside the envelope, and you have a moisture load in the air, all it's going to do is condense onto that duct system. And you could do a great job of insulating it, but even if it's a 1 to 2 to 3 degrees difference, that delta will allow condensation to find that duct pathway. If you keep everything inside the envelope, all is good as far as I'm concerned. But the challenge is keeping it in the envelope. I can send a 3-inch hole through the wall for your ductless heat pump and put your system right on the wall, or in a small space in the ceiling, versus sending it through the attic space or the crawl space. I know in my house I have gas furnace as well, but all my ducts are down in my crawl space, and they're all R8. So when it's it's insulated with an R8. So when it's cold out, the biggest heat load, the biggest delta is pushing through my uninsulated space. So I wind up heating up that lower area more so than any other thing. And if you look at, I'm going to jump back here. I'm sorry, folks. It's kind of hard on your eyes, but when you look at this infrared, if you look at that, that's the furnace register. That's the second coldest space in my house right now. So I just, I'm considering just taking all that out. My furnace came on once last year when it was down in the 20s. That was it. I never used my furnace, and it dropped my energy bill $100 a month in the wintertime to go to ductless. So there's just really no reason to have that giant popsicle sitting on my floor, and I've got 17 of those popsicles in my house. So anyway, so that's my story there. I'm good if it stays inside the insulated space. If you wanted to do a ducted, that low profile ducted needs to be either inside the insulated space or very close to it with a lot of insulation over the top, because I want to keep the heat in the house.
Ken, would you also agree that going to one of these systems, for a gas furnace, you're talking about having combustion in the house, you're talking about having to vent that combustion, which can put another hole into the house, and then reduce your air changes per hour, or increase them. So could you see systems like this also, increasing maybe the envelope efficiency to another, as well as increasing your combustion and potential health issues?
So I'm sorry, Brett, but you were breaking up there. So when we come to combustion issues, first, obviously the ductless heat pump doesn't have a combustion a value. There's no value there's no combustion. It's just an expansion of gas and contraction of gas. So that doesn't become an issue as far as that's concerned. It also doesn't output, for example, any flame has a carbon output or a PP 2.5 output, and you won't have that either. You tend to be able to keep your envelope much tighter with the ductless because you're not going in and out, and I'm not sure if I answered the whole entire question there, but because I wasn't hearing it very well.
Well, it was a very expensive question, and I was just saying too. The question is the pros and cons of replacing existing gas furnace with ducts. With duct systems. I think between actually just more questions on that, we can get to those. So, but we have a lot more coming in here, so let's move on. So this next one we've got here is, when using DHP in climates primarily for heating, is there any difference on guidance for where to place the wall mount unit compared to a climate where it's primarily going to be used for cooling?
Well, not so much. And what happens, the wall mounts, typically we wind up putting the wall mount on the exterior wall because I want to heat the interior walls. I want to get that's the biggest mass that I want. The other function about the exterior wall is that these all require a condensate drain, and from a cost perspective, I can put that condensate drain on the exterior wall and not have to put a pump on there. If I move that wall or that wall mount unit to the interior, then the condensate drain will add cost to the install. It's not a huge cost, it's just a cost. And the condensate drain, when it comes on, your occupant will hear that. So it's not, you know, totally invisible, that part of the process. Now, the cassette styles, for example, you know, I have got guys that they're building big houses, and they have like a balcony with the bedroom areas above the balcony, off the balcony, and they put the cassettes right above the balcony. So in the summertime, when you have that heat load, that cassette will keep that room nice. It'll take the edge off that room, if you will. And remember that cold air drops to the floor, so the cold air falls over the balcony as well, and cools off the lower floors at the same time. And then because it's a 360-degree distribution, as long as the bedroom doors are open, the bedrooms will stay cool as well. Same thing with the heat load. The heat load, although the heat load stays on top, it has to pressurize itself down, but the upper bedrooms stay very comfortable with a single cassette instead of trying to do wall mounts in each room. I'm not a huge advocate of putting wall mounts in every room, and one of the challenges with ductless is, well, let's step back. It's not even a challenge with ductless. It's the challenge with building a good house. So it used to be, if you were doing a 7 air change per hour house, the HVAC guys would take a swag and they'd say you need about 25 BTUs per square foot. So if you had a 2,000 square foot house, you'd need 50,000 BTUs. But now, if you're building a good house and you're 3 air changes or less, the number's about 6 BTUs per square foot. So now 2,000 square feet, you need about, 12,000 BTUs to heat the whole house. So what happens is these rooms become very small, and you put a head in there in that individual room, and it's hard to keep that temperature down. It wants to cycle up and down all the time because it has such great heat output or great capability of output. Typically with a wall unit, or with any of the units, I should say, the indoor units, you can get down to about 20% of the rated value. So a 12K head, 12,000 BTU head, you can get down to about 2,400 BTUs. The challenge is, if it's 50 degrees outside, you might only need 600 or 700 BTUs. So to keep that room pretty darn comfortable. So you have to kind of measure, how big that head. It's not always about having the great, putting a great big head in every room and calling it good. Sometimes you can overdo those. So the other thing about layout, when I talk about the ductless heads, is in bedrooms in particular, I try not to have the ductless head so that it blows directly on the occupant's sleeping area. So, if the bed is going to be right below the head and it goes into heating mode typically blows the warm air down, and it blows the air-conditioned air up. The idea being heated air going down will go down and sweep out and then rise. The air-conditioned air will go out over the top. It'll sweep out and fall down. But if I have that heating load on and I'm blowing it right at you on the bed, you're not going to be comfortable. You're not going to be happy with that. So I try not to point it right where those occupants are going to be sleeping. That's probably the biggest thing I do with bedroom stuff, is managing the airflow in the bedroom.
Great, thanks, Ken. Another question that came in is, are there any special considerations about permitting ductless heat pumps within cities? What are the things that they might be looking for?
So permitting-wise, the biggest thing I come across is that, obviously the ductless heat pumps are a 208 voltage, 240 voltage. And then you're going to have within 25 feet, a 120-volt outlet for service reasons. But it'll have to be on a pad, or in the snowy regions, it's got to be it should be lifted. It should be lifted above what the potential snow level is. And I don't know if that's a code requirement or it's just a common sense requirement. I know when I did projects in Juneau, and we lifted them all 3 feet just because. The ones we did in Kotzebue, we actually put the outdoor condenser on the wall just below the attic under the eave so that they never saw basically a direct snow content. It'd have to be coming in sideways at them. And then the other consideration you get is, so one of the downsides, and I don't have a problem telling people the downsides of ductless heat pumps, but when it gets really cold, when it goes below like 32 degrees, you're going to start seeing what they call a defrost cycle. And if you're unused to the ductless heat pumps, the defrost cycle will essentially what happens is it goes from heating mode, it shuts all the indoor louvers, turns all the indoor fans off, and then it reverses the system into air conditioning mode and then runs at high speed. I mean, it just as much as it can, fast as it can go, and blows hot air across that outdoor condenser to melt any ice that may have formed. Remember, if you're putting heat in your house, you're putting cooling air, cold air outside the condenser. So it'll reverse that process, blow cranking hot air out past the condenser and blow all that ice away from the condenser so it can have airflow. So literally, I've seen ice flows come out of the outside of that condenser in cold climates. So you have to be conscious of what's going to happen in the defrost mode, and do you have room to get that moisture away from the outdoor condenser? And that's more of a common sense deal. The other thing I see is we did a project with a housing authority here in the Washington area, and they called me up and they said, yeah, we need you to come look. We've got some low charge. So a low charge error is where the gas leaks out for whatever reason. And honestly, 1 in 40 applications, your installer installs 40 applications. One of them, within 2 years, he'll have a low charge error code, and he'll have to go out and check the terminations because they're using extremely high pressures, 250 pounds or more, to move, gas and liquid back and forth through the suction and gas pipes. So 1 in 40 will come back with a low charge. But I went out to this site, and of course, there's kids out there playing King of the Mountain on the condensers, and they're using the condenser pipes as, as a step to get up to the top of the condenser. And I'm shaking my head going, you guys, this is a problem. And so in a lot of multifamily projects, while it's not code required, I've seen them put some fencing or some gating around that so that you don't have that kind of challenge. So that's the only thing is, you got to meet your electrical code, and there's going to be a certain pad required so that the thing doesn't tip over. In some communities, in Washington, in the city of Seattle, they have an earthquake requirement. You have to put an earthquake strap on the unit so that they don't tip over in the event of an earthquake. I don't know if they have that in California. They probably do now, in multifamily in particular. So, and I was going to say about the defrost mode, that's my only concern when I see these things attached to the wall, because you can mount them on the wall. I'm not a fan of that, because when it does go into defrost, it will resonate. If it's attached to a 2x6 stud, or a series of studs, it's still going to resonate throughout the house. When it's on a pad, you would barely notice it if it was outside your bedroom. So, what's our next one?
Yeah, I got 2 questions from the same person. I'm going to kind of merge them together here. And she's saying, well, basically, she's mentioning in her area where she's doing work in Minnesota, local heating contractors don't recommend these types of systems. Is that because they simply just don't know it very well? Is it a performance issue? And overall, what would you recommend for someone in this type of climate, which I believe is, climate zone 6? So, there's probably snow there right now. So.
Well, so first of all, I'm still a proponent of ductless heat pumps, because your time. So one of the things on the multi-zones, most of your multi-zone systems will literally lock themselves out at -4 degrees. So at -4 degrees, you would be left without, right? So obviously you want to make sure it's a redundant system. However, it will make you money. That multi-zone system will still make you money from from probably 25 degrees up to 55 degrees. So for that reason alone, I think it still has a better value than just a simple gas furnace all by itself, as well as you get the air conditioning in the summertime. And even here in Washington, we use air conditioning very little. However, I can tell you at night, when it's time to go to bed, I turn the air conditioning on because I need to sleep at night. I mean, that's at the end of the day, I just want to be able to sleep at night. And that feature by itself has paid off for me emotionally, even though, you know, it pays off for me economically on my energy bill. That by itself in the summertime was a huge advantage. But a lot of these units will lock out at -4 degrees. The new single head systems, and Panasonic has them, Mitsubishi has them, Fujitsu, Daikin, we all have these what they call low ambient. They either lock out at 15 degrees or they don't lock out at all. And then on our systems, we'll have supplemental heat capability. So the supplemental heat on these low ambients means that when I get more of a 4-degree delta of the air going through the indoor unit, it'll activate a baseboard heater or a secondary heat source, regardless of what it is. You can run that to your air handler, you can run that to your gas furnace, you could run that to your baseboard, however you want to do that. So it would run down to -15 degrees, and then if it didn't get enough heat out of it, it would just activate a secondary heat source. So it could be used. And then that secondary heat source actually gets locked out at 39 degrees. When the outdoor temperature is 39 degrees or more, that secondary heat gets locked out so that the kids in the bedroom can't turn it up to 85 degrees, and all of a sudden the baseboard heaters kick on too and everything. So the whole low temperature thing is manageable. You got to use the right equipment. There's no question about that. And you have to make sure that, you know, if there's some kind of redundancy that will allow you to, you know, activate a secondary heat source when it gets down to that cold point. And that is the rub with ductless heat pumps. The colder it gets outside, and you saw that on the on that COP report, the lower the BTU output is. So that's the answer.
So Ken, would you say what 2 ways to help would be just, you know, obviously, and the folks in Minnesota do some great work getting that house tightness down, but, you know, just continuing to get that, you know, that air change hour way down, and making sure you're using, you know, a lot of R value in the walls, windows, ceiling in the attic, making that house a little bit tighter. And then, you know, you were mentioning earlier bringing in the ERV system to temper the air. I mean, between those 2 different things, that should really help make more sense.
Well, yeah. So the ERV, one of the caveats about an ERV and an HRV is that when it goes below temperature, they'll literally. So the ERVs when it goes below 35 degrees closes the outdoor air, closes a damper to the outdoor air. So now it becomes an exhaust only. An HRV, and this is a problem with an HRVs. This is one of the issues they're having in Alaska, by the way, in this cold climate stuff. They have a ton of HRVs out there, and they're finding big problems with the HRVs because in the wintertime it goes into recirc mode. So recirc simply means it recirculates the air in the house, and it's not bringing any fresh air in. So they're having big problems with, you know, get out to the villages, and every weekend when the clinic comes in on Saturdays, all these kids are lined up with bronchiolitis and pneumonia because, you know, there's 2 things you do in Alaska in the wintertime, and one of them's cook and the other one's smoke. So these houses are just full of contaminants that aren't being moved, and they build a tight house there as well. So the ERV simply closes the supply air damper and allows it to become an exhaust-only strategy, which is still better than a not strategy. But the answer is yes. You tighten the envelope up, you do the right things right, and that the ductless heat pumps will take care of you. In that when it goes below 25 degrees, though, you'll want to have some sort of a supplemental heat source and not a fireplace. I'm not an advocate for fireplaces. I think wood stoves are probably the least efficient heat source that you can imagine. So I don't know if I answered that question for you, but that's kind of how I feel about that. You tighten it up, you do your ERV, that mitigates during non-freezing temperatures, but the ERV will go into exhaust only, which is what you still have to have. And remember, if I take 30 CFM of air out of your house, regardless of whether it's an ERV or an exhaust only fan, you got 30 CFM coming in. So you will not vacuum your house. You will not suck the windows in. So So yeah, so I guess that reheating component becomes non-existent when it gets to a certain temperature because all of the systems shut themselves off.
Sure. Well, it's a little bit past 1 o'clock here. For those of you tuning in live, I did drop in the GBCI number into the chat box if you need it. If you don't see it, please let me know. Also, there should be a survey coming out to you. And if you have it, if you want, we still have some more time for some questions, so feel free to throw them in. Otherwise, thanks for joining us. For those of you listening on demand to the recorded session, so I'm not talking to any of you right now, please take your 10 questions CEU quiz at the end of this session to pick up your continuing education. Okay, and we're a little bit over 1 o'clock. I don't see any other questions here other than the GBCI number. I'll put that in there. Ken, where can people get some more information? Where can they contact you at? Where can they go to a website and find out more?
Well, you can certainly reach me at my email address there at Panasonic. I think that there's a lot of great information out there. If you just want to Google it, when you start looking for specifics, though, I think that AHRI website is the most critical one. Once you define what your requirements are, the AHRI website can help you identify the products that will meet that requirement. And then the other thing is, I would talk to your local guys. I mean, they certainly, your local installers and contractors, they may not always get the building science component of it, but they can certainly tell you the tendencies of the devices that they're installing. And I think that's important to make sure that you understand ductless heat pumps are different from a gas furnace, are different from radiant heat. And you want to understand or at least know in advance what you're getting into when you do that. Once you figure them out and you're comfortable with them, it's pretty remarkable. They're pretty invisible. But there's other things. Also each of those indoor units is going to have a filter. One of the things I talk to builders about is to quit putting these stinking wall units up 14 feet in the air where, in a retired facility where the people can't reach the filters to change the filters, because the filters do get dirty. So there's other things. But I would certainly advocate you reach out to me and or your local heating and contracting professional, and they can tell you all sorts of things. So.
Great, Ken. Well, thanks for your time. Thanks, everyone, for joining us, and we'll catch you next week.
All right, Brett. Good day. Thank you, everybody.